Hello everybody, this is Hansen, and this is the second playlist I created for SOA examination preparation. And this playlist is specifically about the financial mathematics in or FM. So this video it's going to be the one for you if you have done all the studying of the manual. So basically you understand every single knowledge and you just want to practice some questions. So every time I'm going to provide 5 questions, and for each of the questions, I'm going to let you guys pause the video and time yourself for 5 minutes and see if you guys can figure the question out. And after that, I will go over the question. So today, we're going to go over 5 questions in FM, which are sample questions 345, 119, 51, 118, and 115. And let's get started. So please pause the video, spend 5 minutes, and see if you can figure this out. Okay, so let's talk about the question. This problem is basically about bonds. So this is an N-year bond with the annual coupon rate of R%, and it has the following characteristics. So the face amount is 980. So the face amount here is the number which is used for coupon calculation. So in other words, the coupon annually, it's going to be the R% of the face amount, which is $980. And the coupon is basically the issuer, the money the issuer is going to give you for free every single year for holding your money. And the second condition is that the coupons are paid semi-annually, and the amount is 49. And this is some pretty useful information because if they pay you 49 half a year, which means that they will pay you 49 plus 49, which equals to 98 in 1 year. So the coupon amount annually will be exactly $98. And we also know that that's exactly R% of the face amount, so we can find R. So the R% of the face amount will be something like this, and that equals to 98 exactly. And that gives us R equals to 10 immediately. So we can actually find that the coupon rate is 10%. Now let's go over the third condition. We haven't read all the questions yet. So the annual nominal yield rate convertible semi-annually is R plus 1.8%. In this case, this is going to be 11.8% since R equals to 10. And the convertible here is the key. So convertible means semi-annually means that I can just convert it to the interest rate of half a year by just dividing it by 2. So the effective interest rate of half a year, it's going to be 11.8% divided by 2, and that's going to be 5.9%. And that's our interest for half the year. And because of that, I can also find the discount factor for half a year, which is simply going to be 1 over 1 plus I. And this equals to 0.9443. So that's the discount factor, which we can use to basically find the present value of all the cash flows. Okay, and the fourth condition is the purchase price, which can be also considered as the PV of these cash flows. So if I convert all the coupons back and the redemption value. So let me talk about the redemption value first. So the redemption value is the amount the issuer is going to give you right at the end of the bond. So basically, if you purchase this bond after N years, it's going to give you the last piece of the coupon And at the same time, it's going to give you the redemption, which is exactly $1,000. So it's a pretty decent deal. Okay, so basically, if I convert all the cash flows back to time zero when the bond was bought, the exactly PV, the present value of that, it's going to be $915.7. And because of that, I can try to set up an equation. So let's see. So $915.7, that's going to equal to, so let's try and find the present values of all the coupons. So every half a year, they are going to give the buyer $49 per coupon, and this is basically the payment, and all the cash flows they forms an annuity. So uh, the annuities, it's going to be since they're going to give you coupons every half year, and it is an n-year bond, which means that they're going to give the buyer 2n times with the interest of 0.059. So the interest of half a year. So that's all the that's the PV for all the coupons. And don't forget, we still have the redemption, which is $1,000 in after 10 years. Oh, I mean, after n years. And that's why we need to multiply this the by the discount factor V. And since the discount factor is the discount factor for half a year, which means that I need to raise this to the power of 2n. Okay, so the equation is set, and we just need to solve for this equation. So we all know that for a general annuity, this is going to be 1 minus v to the power of n over I, where I is the interest rate and the v is the discount factor. So by this equation, I can simplify everything for a bit. So this number, it's going to be 49 times 1 minus v to the power of n. So for now, let's just keep v. I mean, I can totally write v as something like this, but I want to make things simpler. So maybe let's just write this as v for now. And for my I can just write it down, which is 0.059. Okay, so that's the all the coupons. And finally, we have 1,000 to the times v to the power of 2n. Okay, very nice. So maybe I can simplify this for a bit and do some simplifications. And this is going to, I can simplify everything for a bit. And eventually I should, oh, I think I made a mistake. It should be 2n because there are exactly 2n payments in here. So both here and here is going to be 2n. Okay, so maybe we can just treat v to the power of 2n as some variable, and we just simplify this for a bit, and eventually we should be able to get v to the power of 2n equals to 0.50263, which is pretty nice. And we also know that v, now it's time to substitute v, 0.9443 to the power of 2n equals to this decimal. And whenever we want to solve for the exponent, we usually want to take the logs or the ln or logs of any base on both sides. In this case, I can do ln so that I can take my exponents down. So it's a pretty decent technique. So 2n equals to log of 0.50263 and log of 0.9443, which by the calculator equals to 11.9444. And I can divide everything by 2 so that I can get n equals to 5.9722, which approximately equals to 4. Oh, I mean 6. Okay, so this is how we do these kind of questions. So basically, for a bond, we always need to keep in mind that if I convert all my cash flows and finally the redemption back to time zero, it should equals to the purchase price, and that's where we can set up the equation. Let's go ahead and jump to the next question, question 119. So please pause the video and spend 5 minutes. Okay, so let's talk about this question. So this question is basically about, so this is a perpetuity. And more important is that it's an increasing perpetuity. Increasing perpetuity. So basically, the increasing here means that the payments are increasing. So each payment is 200 larger than the preceding payment right after the third payment. And the perpetuity means that the payment goes forever. So we basically want to, so the present values are given for this annuity, and we just need to find the effective rate of interest, I, annually. Okay, so since the payments are made half a year, so every half a year, and basically the first two payments are 300, and after the second payment, it's going to be $200 more. So it's basically, you know, oh, and this is, so notice that this is a perpetuity due. So the due here means that the buyers will, so let's assume I want to buy this, I will receive the first payment immediately at time zero. And the last payment, oh, we don't actually get a last payment, but if this is not a perpetuity, then the last payment will happen at the time of n-1 instead of the n. Okay, so basically on time zero, I'm going to, let's assume the units are years. So at time zero, I'm going to get the 300s immediately. And after half a year, I'm going to get another 300. And after half a year, I'm going to get 200s more than the previous one. So I'll get 500. Half a year later, I'll get 700. Half a year later, I'll get 900. And it goes on. And we know that if I convert everything back to time zero, the PV of all of these cash flows will be exactly 475,000. And we want to determine the effective interest rate annually. Okay, so let's try and set up an equation. But before we do that, since each payments are happening half a year, which means that we maybe the I here, it's not the best things to deal with. So in fact, we want to find the effective interest rate semi-annually first, and then we can use it to find I. So maybe I can let J be the effective interest rate semi-annually. So let's find J first, because we can just treat them as half a year and half a year like that. And don't forget, since they are both the effective interest rate, this implies that 1 plus I equals to 1 plus J squared. Okay, so now we can try and find our J, and maybe let's get our variables straight. Let V, the discount factor, be the discount factor for half a year. So we're using J instead of I's here. Okay, so now we're ready to set up our equation. This is going to be 475,000 equals to, let's see, so I get 300s right now, I get 300s half a year after, and I'm going to convert it back by V, and next payment is 500 V squared and 700 V cubed, and it goes on forever. Okay, and now let's see. Let's make everything simpler for a bit. Maybe we can, for example, I can divide both sides by 500 because I don't want so many zeros. I can totally do that. Okay, and what else can we do? Well, I can, for example, I can maybe factor a 3 out. 1 plus v squared plus blah blah blah. And notice that for all the terms here, there are going to be more than 3, so I need to add them back, which will be 2v squared plus, so the next one will be, I believe, 4v cubed plus blah 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 blah. Okay, so then I need to take a, I believe I can take a 2v squared out for the second component. So plus 2v squared, and what's left is just v, actually 1. 1 plus 2v squared plus, and let me write a few terms to understand what these are. 3v cubed plus 4b to the power 4, and so on. Okay, so if I can understand what these two equals to, then I'll be happy. And there are formulas about that. So I'm going to write them down. So 1 plus v squared plus v cubed plus blah blah blah. This, we know this from calculus. This equals to 1 over 1 minus v. Okay, so basically, if you are not familiar with this one, it's also in the manual, or it's also in some calculus books. So if you are not super familiar with the calculus, I would highly recommend that you review about the calculus knowledge, and then go back to study the manual again, because this manual requires a lot of calculus to do that, because we are actuaries and mathematics is basically what we have to do. Okay, and the interesting part is the second one, because that's not any of the calculus result. 1 plus 2v squared plus 3v cubed plus blah blah blah. So basically the coefficient is increasing and the powers is increasing too. And how do I find this result? Well, I'm going to write down the result first, and maybe I'm going to let you guys prove it on your own. So basically, this is 1 over 1 minus v squared. And you guys may wonder, oh, why is that? This is such an weird result. Well, so one way to think about this is that we can just write of these as S. Let's assume this is S, and we consider SV. So SV is going to be v plus 2v cubed plus 3v to the power of 4 plus blah blah blah. And then we find the difference, S minus SV. And this is going to be, if we get everything correctly, it's going to be 1 plus v squared plus v to the power 3, and it goes on forever, and basically never stops, and we know about this already. And basically S times 1 minus v, it's going to be 1 over 1 minus v. Divide everything by 1 minus v, and that will give us this. So yes, this is pretty straightforward. Okay, so we know about these two formulas, and we can just plug them in. So I'll get 1750 equals to 3 times, maybe I can write 3 on the top, 3 over 1 minus v. and plus 2n squared times 1 over 1 minus v squared. Okay, so these are sort of not that. So basically, now maybe it's a good time to replace. So since that's also so since v equals to 1 over 1 plus j, and I should be able to get that 1 minus v equals to j over 1 plus j, since 1 can be written as 1 plus j over 1 plus j. Okay, and we can replace that, and we can write them in forms of j's, and eventually rearrange for a bit, and I'll get a quadratic equation, which is 4747j squared minus 3j minus 2 equals to 0. And I don't think there's any ways to factor this, to be honest, so we will have to use the quadratic formula. And by the way, we can use the calculators anyways. So let's just use a calculator. So negative b plus or minus b squared minus 4ac over 2a. Okay, and it turns out that the negative, if I do just the negative here, then this is so this is probably not going to be the best idea here, because it's going to become a negative number, I believe. Yes, it's going to be a negative number, and that doesn't really make sense because the interest rates are usually positive. So if you now we can just use the calculator to do that, and we will get j equals to 0.2208. Okay, and since j equals to that, we can use it to find our I. So 1 plus I equals to 1.0208 squared, and we can just use it to use a calculator to find I, which is I equals to 0.0421. So the answer should be E. Okay, so I'm sorry that I didn't do most of the details here because the lack of the space. But the important part is really these two things. So basically, if we are able to rewrite these two parts from in this increasing perpetuity, then the others are all piece of cake. We can use a calculator to do that. Okay, so very nice. Let's go ahead and move to the next question, which is question 51. Okay, so basically, let's talk about this. This question, it's about a duration, which is the last chapter of financial mathematics. I mean, one of the content in the last chapter. So there are two things we need to know. The first one is the first order modifier approximation. So we need to know about the formula. And also we need to know about the relationship between the modified duration and the Macaulay duration, because the question, it's given the Macaulay duration. Okay, so basically the DMAC, I'm going to use DMAC to represent the Macaulay duration. In this case, it is exactly 7.959. And there are two things we need to know. So the first one is the relationship between the modified duration and the Macaulay duration. So D mod, the modified duration, equals to exactly the Macaulay duration divided by 1 plus I. Okay, so basically, since we know about the Macaulay already, this equals to 7.959 over 1 plus I, so 1.072. And this is going to be 7.4244. Okay, So now, since we have the DMod, we can use the DMod to basically do a first order modified approximation to find the change of the price. So after I find the change of the price, I should be able to predict the new price of the bond. So, and that requires the second thing, which is the formula for the first order modified approximation, which is the change of the price over the price. It's approximately equal to the negative d mod times the change of the interest. So this is the second thing we need to memorize. And let's see. So since the interest rate rise to 8%, this means that the interest rate changes from 7.2% to 8%. And that change is exactly plus so 0.008. In other words, 0.8%. So this is our change of interest. Okay, so I think we already have everything we need. Let's see. So the change of the price over the price. So notice that the price here is the original price, 1,000. It's approximately equals to the negative d mod times the change of the interest. Okay, and we can use the calculator to find change of the price, which is going to be, maybe let me take out my calculator. Nice. So the change of the price is a negative number, indicating that the price is dropping. And of course, the price is dropping because all the options are less than 1,000. So we just need to find the new price. So the new price obviously is going to be the original price and minus the amount of dropping. And this is going to be exactly 940, 6045. And the answer should be A. Okay, so for this one, we don't need to know about the exact definition of duration. We only need to know about the relationship between d mod and d mac, and also we need to remember the first order modified approximation to find the price change. However, you guys still need to know about the true definition of DMAC. So it's basically the weighted average of some certain cash flow. So, but since this is not related to the question, maybe I shouldn't talk about that here. Okay, so let's go ahead and move to let's see, there are two more questions. So let's go ahead and pause the video. This is the second last question. Okay, so let's go ahead and look at this question. So this one it's also about increasing annuity. Increasing annuity. Okay, so basically, the interesting thing is that the investor it's going to receive 2 at the end of the first month, and right after that, I mean, I read right after each month, it's going to receive 2 more. So the each month thereafter. So basically, so this is the first month. I'm going to receive 2. The second month, I will receive 4. The third month, I'll receive 6. And the fourth month, I'll receive 8. Okay, and let's see, the annual nominal interest rate of 12% convertible. So I like the convertible here because of this word, I can always convert it very simply by just dividing. So this is monthly, so divide by 12. So 12% divided by 12, it's going to give us the effective interest rate monthly. So this is going to be 1% per month. Okay, so maybe I can use J to stand for the amount, the effective interest rate per month. That's going to be 0.01. And I can also find the discount factor, V, of the monthly by finding 1 over 1 plus J. And this is going to be 0.9901. Okay, and now we want to find X, and we know that X equals to a bunch of cash flows. So basically we have 2, and I need to convert it to times 0 plus 4V plus 6V. I mean 4V squared and 6V cubed plus 8V to the power of 4. And how many, so let's see, how many payments do we need? Well, let's see, this is a 5-year annuity. So basically this is going to last for 5 years. And each of the months is going to pay once. So since there are 12 months in 1 year, then this means that there will be 60 payments. So it's going to continue goes. So basically this is going to entail 120 times V to the power of 60. Okay, so basically there are 60 payments exactly from month 1 to month 60. Okay, so this is like an increasing annuity, and because of that, there's something I probably want to do, and maybe I should just write out the general formula for the formula which will help us solve the question. So k times x to the power of k. So it turns out there's a general formula. And if you guys don't want to memorize this formula, that's totally fine, because I don't memorize the formula as well. I just want to present it to you if you want to do this in a faster way. And if you don't want to have the formula, you can again just use the old trick. If we go back to here, so basically by using this is also going to, and this is infinite. So actually you cannot do that. But if this is finite, if this is finite, then you can again use the old trick. But something bad about the finite is that, so notice that if this is finite and I write this as S and I try to do SV minus S, then everything will go smoothly, but there will be one weird term at the end because this is finite. So the reason why this is simple is that this goes on infinitely and we will never see the last term. But it turns out that the last term, it's super weird. So if this is finite, then the summation will become ugly. So feel free to do that as well. And that's how we get this formula. So enough talk, and I should just write it down. So this basically equals to x minus n plus 1 times x to the power of n plus 1 plus n times x to the power of n plus 2. All over 1 minus x to the power of 2. Okay, so this is, memorizing this formula is not mandatory, but this is definitely going to increase your speed in solving questions like this. Um, so maybe I'm going to leave the proof as the exercise. So we can just use the um, um, S minus SV trick to show that. Okay, so so for now, let's just use the formula right away. And this is going to equal to, let me see. So maybe the best way so far is to take a 2 out so that I can have the form like this. Until 60 v to the power of 60. And the things inside, we can use the formula. This is going to be 2 times v minus, so n plus 1 is 61, v to the power of 61 plus, this is going to be 60 times v to the power of 62. And this is all over 1 minus v squared. Okay, so, and we know about v. V is right here. So, thanks to the calculator, we can just use a calculator. 2475.61702. And the answer should be C. Okay, so basically, this formula is the finite version, which we can use to tackle almost all the increasing annuity problems. So again, feel free to memorize it for the exam. Okay, so let's go ahead and work on the last question, problem 115. So again, let's spend 5 minutes and see if you can tackle this question on your own. Okay, so let me talk about it. So this problem is about the continuous annuity. Continuous annuity. So basically, the formula for continuous annuity, so we like to denote it by A and bar mostly. So this basically stands for continuous annuity for n years. And the formula for this, it's equal to 1 minus e to the power of negative and the force of interest, all over the force of interest. Okay, so for now, so for this one, we don't actually need to memorize the definition of it because we can just solve for it. So notice that the present value of a 20-year continuous annuity of $1 per year. So the $1 per year, it's very decent because I don't need to add any coefficients in front, it's just 1. It's equal to 1.5 times the present value of the 10-year continuous annuity of 1 year per year. Oh, I mean $1 per year. So basically, this is saying that the continuous annuity of 20 years is equal to 1.5 of the continuous annuity of 10 years. According to the formula, 1 minus e to the power of negative 20, the force of interest, over the force of interest, it's equal to 1.5. 1.5 times 1 minus e to the power of negative 10, the force of interest, over the force of interest. And let's see, since because of that, I can multiply both sides by the force of interest and get 1 minus e to the power of negative 20, the force of interest, equal to 1.5 times 1 minus e to the power of negative 10, the force of interest. Okay, so if I want to solve for the force of interest directly, this is probably going to be a hard job. And in actuarial exams, we see these kind of equations all the time. And people wants to, a lot of people don't know how to solve for this um, directly. And honestly, this is just going to be hard to solve immediately. But we can always use some tricks. So notice that there is some relationship between this one and this one. So notice that this one, it's exactly the square. So e to the power of negative 20, the force of interest, it's exactly the square of this one, because if I square that, that's going to be to the power of negative 20, the force of interest. So maybe I can let. So here's the trick. Let x equals to e to the power of negative 10, the force of interest. And that will make this x squared. And this the whole point will become, so everything here will become easy. So 1 minus x squared equals to 1.5 1 minus x. And this is much simpler. So let's see. Um, so so what do I have? 1 minus x squared equals to 1.5 minus 1.5x. And basically I can do x squared minus 1.5x. Okay, and plus 0.5. Okay, I think that's correct. Equals to 0. So maybe 2x squared minus 3x plus 1 equals to 0. Okay, and if I try to solve for this, then let's see. If I use the quadratic formula, negative b plus or minus b squared minus 4ac over 2a, this is going to be 3 plus or minus 9 minus 4 times 2 times 1 over 4. Okay, so let me see. So if I do that, so this is going to be 8, so there will be 1 or 0.5. Okay, and the interesting part is this. The only possibility that e to the power of negative 10, the force of interest, equals to 1 is that the force of interest equals to 0. And that's just impossible. So the only answer correctly will be 0.5. So we have to abandon the 1 here. So the force of interest will never be 0. Okay, so now since this equals to 0.5, this means that I'm going to write it here. So e to the power of 10, the force of interest, equals to 2. Okay, and we can just take logs on both sides, and I'll get the force of interest equals to ln 2 over 10. My horrible writing. Okay, and because of that, and the question is asking for the accumulated value of 7-year continuous annuity. So I think we also need to know about the accumulated value, or the FV of a continuous annuity. So this is going to be e to the power of n times the force of interest minus 1 over the force of interest. So this is another formula for it. And now we're just finding S7. and this is going to be e to the power of 7 times the force of interest minus 1 over the force of interest. Okay, and if I plug in everything and use a calculator, I should be able to get 9.0096. Okay, and that's going to be option D. Okay, so very nice. So I think that's going to be everything for today's section. Thank you very much for watching this video, and I will see you in the next one.